Okay, let's turn to condition 3, the ellipticity property of the bilinear form. So we are going to prove that a of phi is larger than some positive constant c2 multiplied with the square of the norm of phi. And this should be for all phi independent, and c2 is independent of which phi we choose, of course. So we are going to prove this. Okay, then we just do as we did for the second property. We write the left side of this inequality, write it out, and we know that it's this integral by the definition of a, and grad phi multiplied with grad phi is just the absolute value of grad phi square. And here we use that lambda is a function which is strictly larger than some lower bound lambda minus, which is a constant. So, and this is just to find an easier way of estimating this integral, because lambda minus is a constant, so we can put this in front of the integral sign like this. And now we are going to use some trick which is usually associated with the third step. We have to use the Friedrich inequality for the Diriclet problem. For other problems, Poincaré inequality can be used. And let's just recall Friedrich's inequality. It says that the integral of the square of phi is less than some positive constant c0 multiplied with the integral of the square of the gradient of phi. So what we are doing now is to relate this to the norm of the Sobolev norm of phi. So why don't we just add grad phi in the integral here, the square of grad phi? And so what we have done here is to add the integral of the square of grad phi on both sides of this inequality. And then we obtain easily this inequality. And the reason for doing this is that this is now identified as the square of the norm of phi. Recall that when we took the square root of this guy, we obtained the norm. So therefore, when we are not taking the square root, then this must be the square of the norm of phi. So on the right side we have this, on the left side we have this, on the right side we just keep what we had. And now I want to relate this to this integral multiplied with c minus, because we see here something which is very close to what we have down here. So now I divide with c0 plus 1 on both sides, just to get an estimate of the integral of grad phi square. And multiplying with lambda minus on both sides, we see that we get estimate on this term. So here we obtain that the norm, the square of the norm multiplied with this constant is less than this this guy, which we want to estimate. So let's do this on the next page. We just write this once more, and we know from above that this is in fact less than a of phi. Let's go back just to ensure you about this. So here we have that this is less than a phi. phi phi. So when we have an estimate on this, we in fact a lower estimate of this, we now conclude that this must be less than a of phi phi. So then we in fact are very close to proving the third step. We have proved that a of phi phi is less than this constant multiplied with the norm of phi. And letting this constant be equal to this constant C2, then we have proven what we were supposed to prove. So now we also have proved step 3. Step 4 is a little bit easier than step 3, I think. It's connected to the linear form of the functional L of phi. We are going to prove this for all V element in this Sobolev space. And in order to prove this, we do as we have done for both the second step, the third step, write out L of y. We know that it is given by this integral. And using Schwarz inequality in this case also, in fact, a version of it which is more trivial than the vector version we had previous. This we have shown you this before, that the Schwarz inequality takes this form. So then we have the integral of the square of f, and we take the square of this integral multiplied with this integral, the square of this integral. So now we can use, because f is some function, we can choose to let C3, this constant, be equal to the square of this integral. If we are doing this, then we obtain that L of v in the absolute value of it is less than C3 multiplied with this. But as we see, this is not the norm of v here. So we have to add the gradient of v on to this integral, the integral of the square of the gradient of v. And this is no problem because it's, of course, a larger number. The inequality goes in the right direction. And now we are at the position to see that we have proven this inequality, because this is, in fact, the square root of this is, in fact, the norm of v. So now we have proven that the absolute value L of v is less than this new constant C3 defined by this integral multiplied with the norm of v. So then we have proven also this property 4. Now we are in a position to use Lax-Milgram's lemma to see that the Diriclet problem in fact has a unique solution. That was Lax-Milgram's lemma, or theorem if you want. And we also, since property 1 also is satisfied, we know that this is equivalent with the minimum formulation that f of u should be less than f of v for all v element in the space capital V, which in our case was equal to the Sobolev space W0, and where f is the usual functional associated with the Diriclet problem.